everyone. Today we're going to look at the negative binomial distribution, okay? And I'm going to kind of walk you through sort of a scenario, and then we'll look at how this ties into the negative binomial distribution as we go through, or sort of at the end, okay? So just try and follow it, maybe get it down as we're going along, or just sit and watch it to start with, and then come back and pause it, etc., etc., okay? Right, so we're going to think about the binomial distribution. So obviously you know from normal maths that if we have a binomial distribution, then let's call a random variable x is binomially distributed with a number of trials n, and p is the probability of its success. We know that in order for a binomial distribution to be true, p has to be constant, i.e. the probability of success cannot change, and the trials are independent of one another. Okay. So, what we're going to do today, what we're going to consider now is we're going to consider the number of trials that are needed to achieve a number of successes. Okay, so for example, let's say that we want going to roll a dice repeatedly until we've rolled 3 sixes. Okay, then we can say that x represents the number of rolls needed in order to obtain 3 sixes. Okay, so x is our random variable here. Okay. Right, so here we go. We're gonna think about how we are gonna find this x, i.e. the number of rolls needed in order to obtain 3 sixes. Okay, so if we say that the probability that x equals 10 is the probability that the third 6 occurs on the 10th roll. Okay, so because we're saying that we want to achieve 3 sixes and x is the number of rolls needed, so if we've got the probability that x is 10, that says that we get the third 6, which is what we're requiring, on the 10th roll. If that is true, that means that prior to the 10th roll, we'd have needed to get 2 sixes, because the third 6 would have to be on the 10th roll. Okay, so that means that exactly 2 sixes have been rolled in the previous 9 rolls. Okay. Now, obviously, when you are rolling a dice, the probability of getting a 6 when you roll a dice is a 6, okay? And if we're doing 9 rolls, yes, 9 rolls is our number of trials, so we can use a binomial distribution for that, a normal binomial distribution, okay? So here we're saying we've got to have had exactly 2 sixes in 9 rolls, right? So we're looking at a binomial distribution where our number of trials is 9 and our probability is a 6, because the probability of rolling a 6 is a 6. Okay? So we want there to have been 2 sixes in these 9 trials. So we're looking at the probability that x is equal to 2. Okay. Now, if you look in your formula book, you will see this bit in pink here, which is the formula for that. Okay. And this is the formula written down. Now, obviously, you can type that into a calculator. You could do your big calculator and use BPD and get that this probability here that we're ending up with, okay? However, in order to generate our formula for negative binomial, spoiler alert, in order to generate it, we're going to need to use this formula, okay? So I'm just going to use this formula here. So we've got this nx is 9 choose 2, okay? We've got 9 trials, and we want to know the probability that we get 2 successful sixes, okay, times by our probability of success, which is a 6 to the power of x is 2, times by 1 minus our probability of success, i.e. our probability of failure, which is 5 6, to the power of our number of trials take away what we need, so 9 take away 2 is 7, okay, so that is 9 choose 2. Don't forget when you're doing your choose button on your calculator, just by the way, you're going 9 and then shift NCR 2, so 9 choose 2 times a 6 squared. It's a bit irrelevant what we get as our answer here, by the way. I'm just showing you how we do it. Times by 5 6. Sorry, I'm being really slow. 5 6 to the power of 7. Okay, and you get this number here, 0.279081. Okay, irrelevant what that is. I'm just talking you through it. Okay. So what we have just said is that the probability of getting 2 sixes in the first 9 rolls is that. Okay. Now what we're trying to work out is the probability that our third 6 occurs on the 10th roll. So in order for our third 6 to occur on the 10th roll, we need 2 in the first 9 rolls, which is this probability we've just worked out, times by, and we need a 6 on the 10th roll. We need to roll a 6 on the 10th roll. Okay, well, what is the probability of rolling a 6 on the 10th roll? Well, that just means what is the probability of rolling a 6? Doesn't matter what roll it is, that is a 6. Okay, so we've got all of this here, which is just this bit up here. So the probability of rolling 2 6s in the first 9 rolls is this, times by a 6. Now, without calculating that, that is the same as 9 choose 2, and then a 6 squared times a 6 is a 6 cubed, times 5 6 to the 7. Okay, and that is our answer. Okay, so this is an example of negative binomial. Okay, and this formula here is the formula we are going to have to use in our negative binomial. Okay, it's a standard formula. This is us deriving it. This is us making sense of it. Let's think about it as a formula now. Okay, so what this means is, I need to read it all ahead, that for successive trials with a constant probability of success P, the number of trials needed to get R, we use R successes, okay? So we need, I don't know, six fives in 10 rolls or something like that, okay? X is referring to the number of trials needed. This has a negative binomial distribution with the probability function here, okay? The probability that X is equal to X, which is what we just worked out, is this take away 1, our successes take away 1, our probability to the power of our successes, and our failure to the probability of our X minus our R, okay? Now that formula we have just generated by thinking about it logically on the page that we've just done, okay? So if you've got both those down, you can kind of have them comparing, all right? Now there technically isn't really a standard notation for negative binomial, but from now on we will use that X is negative binomially distributed with an RP. R being the number of trials needed to get so many successes, okay? So we want to get 3 4s when we roll a dice, so that would be 3, okay? And the P is obviously your probability. Okay, we're going to do a little example then. Try not to panic about this if it's a bit confusing, just try and roll with it and hopefully we'll get there. Okay, so Poppy is practicing her piano scales. The probability that she completes a scale correctly is 0.4. Okay, so what that tells us is that P is 0.4. She continues practicing until she has completed 4 scales correctly. That means R is 4. That is the number of successes that we would like. Okay, R is 4. So here we've got P is 0.4, R is 4. Find the probability that she completes her 4th correct scale on her 12th attempt. So that means our X is 12. Okay, here we go then. So X is referring to the number of attempts needed to complete 4 scales correctly. This means, don't forget to set up your distribution. You get a mark for setting up your distribution. X is negatively binomially distributed with a R is 4, that's our required successes, and P is our constant probability of success. Okay, we are then going to use this formula up here. Okay, the formula up here, just to remind you, is X minus 1, that's our choose function, times P to the power of R, 1 minus P to the power of X minus R. Okay, so R is 4, X is 12, so we've got 11, choose 3, times our probability, which is 0.4, to the power of our R, which is 4, times 1 minus P, which is 0.6, to the power of 12, take away 4, 8. And you can chuck that in there. Okay? Right, question B. Find the probability that she completes her 4th correct scale on her 10th attempt, given that her first scale was correct. Okay, hold that in your brain. Right, so let's call it a different thing now. We're going to call it Y. So let's say that Y is the number of attempts needed after her first attempt. Okay, so if we know that her first attempt was successful, that means she only needs to get 3 more scales correct. Okay, which means that our R is now 3. Our probability hasn't changed, so our p-value is still 0.4. There's still the same probability that she gets the scale correct. That means that y is negatively binomially distributed with a required number of successes of 3 and 0.4. Now, because she's already done her first attempt, that means if her fourth correct scale is on her 10th attempt, that means we need now, if we're going after her first attempt, her fourth correct scale to be on her 9th attempt, okay? Or her third correct scale in this case, in this scenario, on her 9th, okay? So then you can just do it as you would normally, popping in your formulae, okay? X is 9, so we've got x minus 1 over r minus 1, okay? Times by our probability of success to the power of r, times by our probability of failure to the power of x minus r, gives us that, okay? Right, you should now be, that is negative binomial, you should now be able to do exercise 3C.